In this worked example, I'm going to take you through the basics of hypothesis testing. We are going to be conducting something called a one-sample t-test. So in the one-sample t-test, what we are basically doing is we are testing our sample against some hypothesized population mean. This is unlike a situation where you have two samples, where you are comparing two samples. Here we only have one sample, resulting in a one sample mean, and we are taking that mean and comparing it against a hypothesized value. Okay, so if you are not familiar with hypothesis testing, I would recommend that you watch a video that I recorded on hypothesis testing. That video will take you through the steps for that, and I will attach it on this particular video. Right, so you can click on it and watch that one first. It takes you through hypothesis testing, and it goes through the systematic steps that you follow to conduct a hypothesis test. Okay, so let's get started. What is a one sample t-test? Right, so before we go to the question, let us just discuss what a one sample t-test is. So what a one sample t-test attempts to do is to answer the following question, right? So let's do this. So the one sample t-test. Okay, so the one sample t-test, it answers the question of, is the sample mean statistically different from a hypothesized population mean? Right, so that is the question that we are trying to answer. Right, so is the sample mean, right? So this sample mean, remember, comes from our sample. Right, so we collect a sample from the population and then we get a sample mean. So is that sample mean statistically different from a hypothesized population mean? From a hypothesized population mean. Okay, so that's the question we are trying to answer. And to answer this question, or to conduct a one sample t-test, there are certain assumptions that have to be met in order for the test to be valid at the end of it all. Okay, so those assumptions, we will assume for our case that those assumptions have been met. Okay, so but in order that you understand those assumptions, I'll just go through, or I'll just go over them so that you are aware of those assumptions. So there are three important assumptions that have to be met for the one sample t-test to be valid. Assumptions to be met, number one. Okay, so assumptions. Number one is that the variance, or rather the variable, should be an interval or ratio variable. So the one sample t-test only applies for continuous. So the variable has to be a continuous variable, has to be continuous, right? So we are talking about a level of measurement at which we are working with a ratio. So that's a ratio or interval. So ratio level of measurement or interval level of measurement. Okay. Number two is that the data points must be independent. So let's suppose that we are measuring weight, and we are measuring a series of patients, weights. So patient number one's weight shouldn't affect the next patient's weight. So data points must be independent. Must be independent, right? So which means there is no relationship between any of the data points. Okay, number three, the data has to be approximately normally distributed, right? So data has to be approximately normally distributed. Okay, as close as possible to normal distribution. Okay, so there shouldn't be any significant outliers in our data set. Okay, so those are the important assumptions that have to be met for our t-test to be valid, so that our conclusion at the end of this hypothesis test is one that can be relied on. Okay, so the next part of the question now, let's go to the questions. The first question says, write down the test statistic formula for testing a claim about a one sample mean. Right, so this is a simple one. So for one sample mean, so the formula for that, it depends on whether it's going to be a z-test or a t-test, right? But the formula basically have the same format, right? So z, if it's a z-test, it's equals to x bar, which is our sample mean, minus mu, which is the population mean, the hypothesized population mean, divided by sigma, which is the population standard deviation, right? Sigma over the square root of the sample size. Okay, so in this particular situation, we are assuming, all right, that we know the population standard deviation, all right? But in reality, we know that most of the time, we won't know the population standard deviation. So in practice, we are mostly going to be conducting a t-test, right, instead of a z-test. So the formula now for one sample mean, where we are conducting a t-test, where we don't know the population standard deviation, so that formula is given by x bar, right? So it's still our sample mean minus the hypothesized population mean mu divided by the standard deviation of the sample. So S is the sample standard deviation over the square root of the sample size, right? So the only difference here is here we know we don't know the population standard deviation. We are working with the sample standard deviation that we are using to somehow estimate this population standard deviation. Okay, now we will go on to conduct our hypothesis test, right? So the question here, the B part, right, says the mean age of patients attending your clinic is 40 years. Okay, the mean age of patients attending your clinic is 40 years. So the manager claims that this is not accurate, and as a result, a random sample of 27 patients is picked from the population of patients, and that random sample of 27 patients has a mean age of 44.5. Okay, and 44.5 with a standard deviation, so sample standard deviation of 3.3 years. We are asked to test the manager's claim at an alpha level of 0.05, so a significance level of 0.05. The important thing to note here is, one, we have a one sample of 27 patients, and those 27 patients have a mean weight of 44.5. So this 40 years is the hypothesized population mean. So to do that, we'll take it systematically. So the first thing that we will do is to come up with, okay, so number one is to come up with or to list our hypotheses, right? So hypotheses come in pairs, right? So we have the null hypothesis and the alternative hypothesis. So in this particular case, our null hypothesis, H0, is going to be that the population mean mu, right? Remember that our hypotheses are statements about the population, right? So the population mean is equal to 40. So that is the hypothesized mean is equals to 40 years. And then the alternative hypothesis will be that the population mean mu is different from 40 years, right? So in this particular case, right, we were not given a clue as to whether the claim is that it's greater than or less than, right? So the manager just claims that it is not accurate, right? So he implies that it's different. He or she implies that it's different. So it could be less than or greater than. So for that, since the manager didn't commit to any side, we would say the mean, right, population mean is not equal to 40 years. Okay, so we have our null hypothesis and our alternative hypothesis. So this will result in something called, later on, in something called a two-tail test. So this is a two-tail test. Right, number 2 is to identify our level of significance. So this is easy, it has been given. Okay, so the alpha level, our level of significance is 0.05. Okay, just as a reminder, what this number implies, this 5%, what it implies is it's actually, by definition, is the probability of a type 1 error. The probability of something called a type 1 error. So a type 1 error is the probability, okay, the probability of rejecting, so the probability of rejecting the null hypothesis, given that the null hypothesis is true, right? So if we wrongly, there's a 5% probability of wrongly rejecting this null hypothesis. Okay, so that's what we call a type 1 error. And then step 3, right? Step number 3, we identify our sample statistics. So it's easy, our sample statistics have been given in the question. Okay, so let's just list our sample statistics. We have n, which is the sample size. N here is 27, that's our sample size. We also have the sample mean, which is 44.5 years. And then we have the sample standard deviation, which is 3.3 years. We now move to the part 4 of the question, which is the test statistic. Right, the test statistic is given by the formula, right? So this formula over here is what will help us to calculate the test statistic. So in this instance, our test statistic T is going to be 44, right, which is 44.5, which is our X bar, minus the hypothesized mean, which is 40, divided by 3.3, which is our sample standard deviation, 3.3 over the square root of sample size 27. Okay, so this value will come to, right, so we have 40, so this is going to be 4.5, okay, 4.5 over 0.63509. So this 0.63509 is 33.3 divided by the square root of 27. Okay, so the final answer here is going to be T is equals to 7.09. Okay, 7.09, that's our T value or our test statistic. Okay, so next we calculate our p-value, right? So this is 5, so our p-value, right? So we use this test statistic to determine our p-value, and for that we need the degrees of freedom. Okay, so we need degrees of freedom. So the degrees of freedom for a one sample t-test are given by n minus 1, right? Where n, of course, is the sample size. So we have 27 minus 1, which is 26. So we are working at 26 degrees of freedom. So there are two ways then to make a conclusion on our test statistic. We can either use the p-value method or the critical value method, right? So I will discuss both, starting with the p-value method. So with the p-value method, what we need is to go to the t-distribution and find what p-value corresponds with a t-value of 7.09, right? So I will bring up the t-distribution. So here's our t-distribution. We are working at 26 degrees of freedom. Okay, here we have 26 degrees of freedom right there. So we go across, right, across until we locate 7.09, right? So as you can see, our table doesn't go as far as that, right? So, but that is not a problem, because we can see that at 3.707, right, a t-value of 3.707, the corresponding p-value for that is right there on top. That is the p-value. So that p-value is 0.0005, right? So since the p-values are decreasing, as you can see, they are decreasing as we go to the right. So we are sure that by the time we reach a t-value of 7.09, our p-value will be way less than 0.0005, right? So what this means, therefore, is that we can conclude, right, based on the p-value method, that our p-value, right, our p-value, right, is going to be less than 0.005. So we don't need the exact p-value, right? It's actually 0.0005, right? So we don't need the exact p-value, because we know that if it's less than 0.0005, it means it's less than our alpha level of 0.05. Okay, so the exact p-value is not important. What this means, therefore, is that our p-value is less than our alpha level of 0.05. Okay, and if the p-value is less than 0.05, okay, we conclude that the test is significant. Since we are working with a two-tailed test, okay, so this is something that's important also to note. The alternative hypothesis is the not equal to hypothesis. So this is a two-tailed test, right? So for a two-tailed test, we always double the p-value before we make our conclusion. So we will double our p-value, or multiply our p-value, okay, times 2, right? So even if we do that, because our p-value is less than 0.0005, we are still going to be less than 0.05, even after doubling the p-value. Okay, so what that means is our final conclusion is still the same. Our p-value, right, is going to be less than 0.05, okay, and therefore our decision, okay, so point number 6 there is our decision. So our decision is that we reject. Remember, if the p-value is less than 0.05, we reject the null hypothesis. And then what is our conclusion? Okay, so we have rejected the null hypothesis, right? So what will be our conclusion? So conclusion. So our conclusion will be there is enough evidence provided by the sample, right? So enough evidence provided by our sample to demonstrate that the mean age of patients attending this particular clinic, to demonstrate that the mean age of patients, right, at the clinic is not 40 years, right? It's in fact not equal to 40 years, right? And we can, because our sample had a mean weight of 44.5, we can even extend it to say it may be actually more than or greater than 40 years, okay? But even though our sample is 44.5, the mean of our sample is 44.5, we cannot make that conclusion because that's not what we were testing. Okay, let's discuss the critical value method. Okay, so with the critical value method, okay, so this is the critical value method. Remember, we are conducting a two-tail test. Okay, it's a two-tail test. What we are going to be looking for in the critical value method is a value that we call the critical value. So that value is a t value. Remember that our calculated t value for our sample, our calculated t value is 7.09. So that is our test statistic. Okay, so we want to find a value, and that value is called the critical value. So if we are conducting a two-tail test at an alpha level of 0.05, okay, so it means that this 0.05 probability is going to be split between the right tail and the left tail, such that on the left tail we are going to have 0.025, and then on the right tail we are going to have 0.025. So the critical value will be a number, a t value on the t distribution, where we have an area of 0.025 on the right side of that number, okay, or an area of 0.025 on the left side of that number. Okay, so whatever this number is, it must have an area of 0.025 on the right, or an area of 0.025 on the left. Okay, so remember that this t distribution is symmetrical. So if this number is x, right? If this number is x, or let's use t, if this number is t, this number is going to be negative t. Okay, if this number is a, this number is going to be negative a, because there is symmetry between the two sides. Okay, so let's go to the t distribution now, and then find a number at 26 degrees of freedom, where we have an area of 0.025, right, on the right side, or an area of 0.025 on the left side. Okay, so I'll bring up the t distribution. Okay, t distribution is here. Again, we have 26 degrees of freedom. Okay, 26 degrees of freedom, and we are looking for, if you look at the top, okay, where it says tail probability p, so we are looking for this probability of 0.025. Okay, so this tail probability refers to the fact that 0.025 is the area or the probability on the left tail or on the right tail, like I showed you. Okay, and then we find where, right, this part intersects with our desired degrees of freedom, and we can see that that critical value, that number we are looking for, where we have 26 degrees of freedom with an area of 0.025 on the right tail and an area of 0.025 on the left tail, since we are doing a two-tail test. So that area is, or that value, that critical value is 2.056, right? 2.056. So 2.056 is our critical value. And then on this side, it will be negative 2.056. Now, what this means is beyond this critical value, right? This area here is called the critical region. Okay, so this is the critical region. And the reason for that is if the t value, our calculated t value from the sample is greater than our critical value and it falls within this critical region, then we reject the null hypothesis. So this is an area, right? It's an area of rejection. So we reject the null hypothesis, right? So similarly on the left side, if our calculated t statistic or test statistic is, right, less than minus 2.056, less than our critical value, then it will fall in this area, right? Which is, again, it is the critical region, right? On the left side, it's the critical region, and also it's an area where we reject the null hypothesis, right? So you can see that our value, calculated t value, is 7.09. So it's not in this region. So this region here is called the acceptance region. So this is where we fail to reject or accept, right? Although we never say accept, we fail to reject the null hypothesis. Now, for our particular situation, our t value is 7.09, which is way beyond way greater than 2.056. So it's way in this area here. Okay, so it means that it is in the rejection region. It is in the critical region, and therefore our conclusion is, right, so our t value is equals to 7.09, and this t value is greater, right, than 2.056, which is the critical value, greater than the critical value, and therefore our decision, okay, our decision will be that we reject the null hypothesis, okay, just as we did with the p-value. So you can see that either you use the p-value or you use the critical value method, your conclusion and your decision and your conclusion in the end is going to be the same. So there is consistency between the two, and generally you can choose, right? If you are not instructed, you can choose whether you want to use the critical value method or the p-value method. So that's our decision, and then our conclusion will be the same, that there is not enough evidence, or rather there is enough evidence provided by our sample to demonstrate that the mean age of patients at the clinic is in fact not equal to 40 years. It could be greater than 40 years because our sample mean is 44.5.